Alrighty. So, if you watched the video that I had just posted earlier, I was working through some of my quantum mechanics homework problems and I ended up getting it wrong. However, the good news is the only reason I got it wrong was because I copied down the form of the operator incorrectly, which has been bugging me all night that I did that because as soon as I finished the video, I realized it. And ended up getting some wonky stuff when I went through the solution. However, all my derivation steps were correct, but now what I'm going to do is I'm going to go ahead and do it correctly. Um, and what I'm also going to do on top of that is, so what we're going to do now is we're going to derive the ground state wave function of the harmonic oscillator in momentum space. And then what I'm going to do is I'm going to take that ground state momentum space wave function and I'm going to use a Fourier transform and I'm going to transform it into position space. Then what I'm going to do is I'm going to use the same type of derivation to derive the ground state of the position space wave function in position space and check that the form of those or the form of that matches what I got from my Fourier transform, and that will be enough to hopefully convince you and me that everything went as it was supposed to. So hopefully my cat stops playing with this box over here so that doesn't mess with the video noise. Hey, sweetheart. I'm going to move you to the other room. Give me one sec, guys. Can't be making noise during my video, sweetheart. People are trying to listen to the quantum mechanics. So, all right. So, here we go. So, the correct form of my A operator, which is the lowering operator, is the square root of m omega over 2h bar times the position operator plus I, not h bar, over m omega times the momentum operator. And what we're going to do is we're going to make use of the fact that the lowering operator acting on the ground state yields 0. And what that means is that if we take and sandwich the lowering operator between the bra P and the ground state ket, that is also 0. So this will allow us to derive a differential equation, which we can solve for a Gaussian exponential, as you'll soon see. And then we'll normalize that and then do some Fourier transforming and then see where we're at. So here we go. So this whole A operator is going to operate on the momentum space wave function for the ground state of the harmonic oscillator. So I'm going to go ahead and call this thing, this inner product of P and the ground state, I'm going to call that phi. And now what I'm going to do is I'm going to write down the momentum space representation of the position operator x hat, which is going to be I h bar times ddp, and the momentum space operator, the momentum operator in momentum space is just going to be p. So this is very similar to how in position space the x operator or position operator is just x, and the momentum operator is h bar over I, or minus I h bar, times d dx. So you can actually get these operators in the different bases by using Fourier transforms as well. But we're going to be sticking with these, where px is going to become p and x is going to become I h bar ddp. So let's go ahead and do that. So now we're going to rewrite that we have, and this is all equal to 0. We are going to have the square root of m omega over 2h bar times x plus, almost messed up again, times I h bar ddp plus I over m omega p times phi equals 0. So we'll do some simplification here. We're going to go ahead and kill that constant. So if we divide it over, it'll go away. And we're going to have IH bar d phi dp is equal to, I'm going to move that over essentially. It's going to be minus IP over m omega phi. Okay, so now I'm going to divide over this IH bar, and that'll leave me with d phi dp is equal to, move the IH bar to the denominator over here. I's will cancel. We'll be left with a P over H bar M omega phi, and now we'll separate the variables and solve our differential equation. So this is going to become d phi over phi is equal to P over M omega H bar dp with a minus sign. And now I'm going to integrate both sides. And once I do that, I'm going to get the natural log of phi is equal to minus p squared over m omega h bar. Oops, should be a 2 there. 2 m omega h bar. That's ugly, sorry. H bar plus c. And then I'm going to exponentiate both sides. And so this is going to reduce to e to this thing times e to that thing. This is just a product of exponents. And so what we're going to get, the e will cancel a log over here, and our final form is going to be that phi of p is going to be equal to n, which is where I've just lumped in that e to the c constant, e to the minus p squared over 2m omega h bar. So that is, hopefully, we'll see upon doing the Fourier transform, hopefully the correct form of our momentum space wave function for the ground state of the harmonic oscillator. So now that we've got that, I'm going to go ahead and apply this Fourier transform. So I gotta flip a few pages back in the book because I'm not going to write down the form of the Fourier transform off memory, even though I think I remember it. As earlier taught me, I want to make sure that I'm writing these down from the book to be safe. So what we have is that x bracket psi, which is also just psi of x, just like this is phi of p, is going to be equal to the integral over dp of xp p phi. And so that will become the integral with respect to p of 1 over the square root of 2 pi h bar, which is just the constant that goes along with that xp bracket. And then we'll have e to the ipx over h bar. Yeah, e to the ipx over h bar. And then that will now be multiplied by that p bracket psi, or sorry, p bracket phi, which is just phi of p. And so that's going to be our n. And so I actually will have to normalize this real quick before I do this Fourier transform. But this is the form of the Fourier transform. And then I'll just go ahead and normalize real quick. And then just leave this up here and sub in our n once we find it. So to find n, we're gonna integrate, we're gonna square it and integrate it over all space. So basically what we're doing is we're doing this. And the normalization condition is such that this should equal 1. In other words, if we take the ket phi and we take its inner product with the bra phi, that should be normalized. And so, oh, I'm sorry, this is squared. So what we're going to do is we're going to have the modulus of n squared, the integral over all space of e. So there's a minus p squared still, but now you think about it as like if you square these, this exponential term, it's like basically adding another one to it of the same form. So the 2's will go away because it's like 1/2 plus 1/2. So it'll be p minus p squared over m omega h bar integral with respect to p. And so this is a Gaussian identity. And unlike earlier where I had an I in my exponential, now our exponential constant a is real, which is the condition to use that Gaussian integral identity, which is that this is equal to the square root of pi over a. So we're going to say that a is equal to 1 over m omega h bar. And so we will see that that will bring our square root to be pi m omega h bar. Cool. So, sorry about the noise from my cat. Hey, sweetheart. The people of YouTube don't want to listen to you. I don't know if you guys can hear it, but this mic's probably pretty good, so I'm guessing you can. Anyways, now that we know what n is, I'll go ahead and rewrite this as the square root of pi m omega h bar e to the minus p squared over 2m omega h bar. So there's the form of that. We'll go ahead and slap that in our Fourier transform and see what we get. And then hopefully we'll get that this will properly reduce such that we get the same answer when we derive the position space wave function from first principles, and then I can go to bed. So I probably don't sound as uppity as I did earlier because I just worked for 5 hours. So we'll go ahead and slap that thing in our Fourier transform. We'll have dp 1 over the square root of 2 pi h bar times the square root of pi m omega h bar. So you'll see with cancellations here. E to the minus p squared over 2m omega h bar. So now I'll go ahead and get rid of this. Oh, oops. Need that term. E to the I px over h bar. There's that. Coolio, coolio. So now there's our Fourier transform. And so now we just got to do this ugly integral. It's not that bad, but I'll go ahead and bring the constants out and deal with those later. So square root of pi m omega h bar over the square root 2 pi h bar integral with respect to p. And so this is just a product of exponentials, so we just have to add the exponents. So I'm going to do that off to the side here to reduce things. We're going to have to complete the square and the exponent here. So what we're going to do is we're going to have, I'm going to use exp just to make the notation a little easier. We're going to have exp minus p squared over 2m omega h bar plus I x over h bar p. And the reason I write it up there is so you can see that it's like a quadratic function where the c term is missing. And so because the quadratic is of the form ax squared plus bx plus c. So what we're going to do is clean this thing up by completing the square. And so let me go ahead and grab the formula for that in Appendix D real quick. So the form for completing the square is that ax squared minus bx is equal to a times x minus b over 2a squared minus b squared over 4a. So what I'm going to do to clean this thing up is I'm going to rewrite this exponential as minus a, oh, actually, no, I can lump it all in. I'll just call it AP squared, where A is going to be equal to minus 1 over 2m omega h bar. And I'm going to let the second term just be B times P, where B is going to be Ix over h bar. Cool. So now we can do some fission with this formula. So we're going to rewrite it simply as now we have AP squared plus, oop, there should be a minus there. I don't have a minus, but I can get one, right? If I factor out something. So I need to let this be a minus, actually. See, it's all about being careful with these forms, guys, because if I do it like this, then I can rewrite this as the exponential of minus AP squared minus BP. It's kind of odd to write it like that, but that's how I'm going to do it, just to get things to be cleaner. I haven't used this trick very much, and it does get very involved when you have these super ugly constants. So hopefully everything will work out like it's supposed to. So now that I have that form, I just have to make sure that I remember that this is a minus A. We're going to let this be that. And so we'll have plus BP, where we're going to now rewrite this here, where I'm going to take out a minus A times P minus B over 2A squared minus B squared over 4A. And so the reason that we do this, as you'll see in a second, is because this is going to reduce our integrand to where we're going to have one exponential piece that is only going to contain x's, and we can pull it out as a constant because we're integrating with respect to p. So if we have an exponential with only x's in it, we're not going to do anything with it because it doesn't have the variable that we're integrating with respect to. And then the thing that's left will have an integral with respect to p, but it's going to be something like this, such that when we do the Gaussian identity, we use the Gaussian identity from the integral, it's just going to spit out a constant. So we're left with a constant times some Gaussian exponential, but it's now a Gaussian exponential with x as its variable. So we've effectively done the Fourier transform and went from the p variable to the x variable. So if I did all this right, that's the form that we should get. So let's see if that's true. So now what I'm going to have is now, if I'm not mistaken, yeah, this is, yeah, see, I gotta be careful here because rewriting all these things just makes things a little bit hard to follow. Sorry, I'm pausing my solution real quick, but I'm going to grab one of my previous homeworks where I did this same trick and see exactly how it looked. Yeah, see, that's what I want to do. That's what I want to do. I don't want to put B in there, right? I want to let B remain. Yeah, and see, it's funny. This is this is a Fourier transform where I went from P to X as well. So this is actually going to be helpful. So I'm going to keep this real quick. So what I'm going to do instead now, let me make sure I'm still recording. Yep, we're good. Okay, So what I'm going to do now is I'm going to rewrite this part as I'm going to keep the form of Ix over h bar here. Like that, such that now when I put this in here, it's going to be Ix over 2a h bar. Yes, that's correct. Ix over 2a h bar. Quantity squared, good. Minus, so now what I'm going to have is I'm going to have an Ix squared, which is going to give me a minus 1 factor, which will make that a plus, which then makes this x squared over h bar squared, right? Because b is Ix over h bar. Let me just do that real quick. So b is equal to Ix over h bar. So now when I do b squared, it's going to be I squared x squared. Hopefully you guys can see that. I know I'm writing a little smaller on this video. That gives us a minus 1, which makes this a plus x squared over h bar squared. Beautiful. And then I'm just going to multiply that by 1 over 4a. Coolio. And so now, what I'm going to have is, I'm going to have, did I lose? Okay, well, we're good. Yep, that's all good. Okay. So, yeah. So what I'm going to do now is I'm going to shift my integrand here in a second. And what I'm going to have is now I'm going to have my constant, which I'll just call n for a second and take care of it later. I'm going to have the exponential piece here, which is only a function of x, like we were stating before, right? And so I'm going to have ne to the x squared. Now here's my answer. Somehow in my answer I've got a negative here, and I don't know where it came from. And I think it has something to do with what I've factored. See, this is like what I'm saying, guys. Things get really tricky really fast, and a minus sign can totally mess me up here. I'm just going to roll with what I've got for the time being and see where it gets me. I guess, well, I guess since I let a be negative, then this would be a minus technically. So maybe that's where it's coming from in my solution. So I'm going to call that a minus. And then the rest of it doesn't change. It'll be 4h bar squared a, where I'll put the a in later. Then we have an integral with respect to p. And now I'm going to shift this integrand. I'm going to say that p prime is equal to p plus Ix over 2a h bar. And then I'm going to shift my integrand from p to p prime. Such that it will give me a minus a p squared inside. This is just a little bit of a trick that my professor taught me. I wish I could tell you more to motivate it. I just know that it's a way to solve effectively. So now I'm going to have the integral of minus a p squared with respect to p, as I already have. And so this becomes there we go. That's all good. Okay. What does the integral end up being? Oh, that's right. The integral just becomes the square root here. It just becomes the square root of pi over minus A. Beautiful. Okay. And then that stays, that sticks around. So now I'm going to just erase over here and keep going. So gut feeling says maybe the final answer is going to be off by a minus sign, but I'm hoping I kept track of everything. And maybe when I'm not so sleep deprived, because I've been awake since 7 a.m., I can solve this and clean everything up and not be kind of sorting through it. But what the heck is going on outside? I don't know. It sounds like someone's dragging a dead body. Sorry, that threw me off, guys. So got ne to the minus x squared over 4h bar a times the square root of pi over a times, jeez, man, we are not even close, guys, unfortunately, pi m omega h bar over square root of 2 pi h bar. Let me see how long we're at right now. We got to be at 20 minutes. Yeah, we're almost at 30. Sorry, guys. It's going to be a long video. But I ain't stopping until we're done. So now we've got to plug in A, and then we can clean this thing up. So now we're going to have ne to the minus x squared. Now, tell me, what was A? A was minus 1. Oh boy, I shouldn't have erased that, guys. Darn it. Well, I can figure it out real quick, because I had minus b squared over 2m omega h bar. Yeah, so that's A right there. So this is 4h bar times 1 over 2m omega h bar. And that's all multiplied by the square root of pi over 1 over 2m omega h bar. But this is supposed to be negative, so that's negative. That's not good, because then we have a square root of negative. See, it's these signs, guys. I'm just going to let it be positive. And I'll motivate that minus sign somewhere else. I'm going to do the solution again. Again, point of these videos is for you guys to see the struggle here. Like, this is what it is. If you want to pursue physics, this is what you're going to be doing. It's 11:30 on a Friday. You ain't going out with your friends. If you really want to get a degree and be good at it, which I do, hopefully, and I hopefully will be good at it one day. I'm all right now. So multiplied by, well, it looks like we're going to get some cancellations there. So that's good. Square root of pi, well, actually, no, we're not, because they're going to cancel here. Omega h bar over square root 2 pi h bar. So now this part's taken care of, barring a normalization. Well, this n is that now, so let me get rid of that. So now we have that. So let's go ahead and get our constant square, and then we can hopefully cancel a bunch of things out, do this derivation from first principles with the operators, and maintain the same form, and I'll go to bed. If not, I will be back. Don't worry. So here we go. So now we've got pi 2m omega h bar to the 1/2 times pi m omega h bar to the 1/2 over 2 pi h bar to the 1/2. So that'll cancel, and that will cancel, and we will be left with pi 2m omega h bar to the 1/2 times m omega to the 1/2 over the square root of 2. Cool. Cool. These will cancel. Nice. So now we have pi to the 1/2. I'm going to write it this way just so I can see it. And you too. Pi to the 1/2, m to the 1/2, omega to the 1/2, h bar to the 1/2 times m to the 1/2, omega to the 1/2. So for the ones that don't have a friend over here, I'll go ahead and put them out. So we'll have pi to the 1/2, h bar to the 1/2. M to the 1/2 times m to the 1/2 is m to the 1/2 plus 1/2, which is just m. Nice. Same thing with omega. So we're going to have the square root of pi h bar times m omega. So that actually ended up cleaning up very nice. So what we're left with for psi of x is square root of pi h bar m omega e to the minus x squared. Oh, I can clean this up too. Bring the 4 on top. So we're going to have 4h bar over 2m omega. I could do this without writing it out, but I'm doing that for you guys. H bar is gone. This will reduce to a 2 up top. So we'll have a 2 over m omega. Cool, and this is divided. So, interesting. So this is actually going to be over 2 over m omega, which means it's actually going to be minus x squared times, let me be careful here, x squared over 2 over m omega, flip, yeah, I was on the track. M omega minus m omega x squared over 2. So that, hopefully, will be the form when we derive first principles using the operators. So I'm going to go ahead and write that down because I'm going to need the whole board to do this derivation. And then hopefully we'll be done before 40 minutes because we're at 33 now. This thing's going to take forever to upload. I don't have a pen handy. It's right here. Let's see. So, what do I have? Psi of x is equal to square root of pi h bar times e to the minus m omega x squared over 2. Okay. Let's see if that's what we get. So, it's going to be the same derivation as what we did in the beginning of the video. However, now we are going to be using the operators in their position space form. So again, we're going to be making use of this. And now we're going to be doing this. So what we're going to have is square root m omega over 2h bar multiplied by x hat plus I over m omega p sub x times x 0, which we're just going to call phi. So now what we're going to do is we're going to say that's all equal to 0. And remember, in the position space, this is going to be x, and this is going to be h bar over I ddx. So we're going to have this constant will go away, so I'm not even going to drag it along. X plus h bar over I times I over m omega. I's cancel, we get h bar over m omega. H bar omega ddx psi equals 0. So now we're going to have that x psi plus h bar over m omega d psi dx is equal to 0, which means d psi dx is equal to xm omega over h bar. Oh, I don't think this is going to work, guys. Well, sorry, lads. Don't think we're going to get it tonight. This wasn't part of the homework. This is just for my own, practice. But I don't think it's going to do it. We'll see. Maybe I'm thinking too soon, but I don't see a 2. I see an M omega. I didn't even have an H bar in my final form, so I guess we're going to see where we're at. So x psi, yeah, so subtract that over. Yeah, I'm subtracting this term over, so it's going to be minus x psi, and then I'm going to divide by that, so I'm multiplying by the reciprocal, so x m omega h bar psi, which leaves us with, oh wait, no, I'm going to get a 2. Oh, I think I got this right, guys, minus an h bar. So I'm going to have to figure out where that freaking h bar went. So d psi over psi is equal to the, I'm going to take out the m omega over h bar. And, oh, wait. No, the h bar, wait, no, hold on. See, now I'm getting delusional. Oh, no, the h bar is not going to cancel. It's there. It's definitely there. I'll just go follow it to conclusion. So I'm going to take the m omega over h bar out. We'll have the integral of x dx. Beautiful. So natural log of psi equals x squared m omega over 2h bar plus c. Exponentiate both sides, and we get that psi of x is equal to n e to the x squared c. I don't even have a, silly me. There's a minus. M omega over 2h bar. So yeah, I'm missing everything. Or I have everything except for this h bar. That's the only thing I'm missing, guys. So maybe those h bars didn't cancel like I thought they did. Somebody catch me, please. So now we'll normalize this thing, and hopefully we'll get the same constant. Then I'll feel a whole lot better and just find that h bar that I somehow threw in the gutter on accident. So this is going to be modulus n squared, integral over space, e to the minus x squared m omega over h bar. Over h bar? Yeah. Yeah, I think so. H bar dx. That's a Gaussian identity. So we're going to have square root. Oh, these. No. See, I'm going to be missing some stuff here, guys. So clearly the Fourier transform went wrong somewhere. That's okay. It's a good practice. That's all that matters. This is definitely getting the brain gears turning. All this has to equal 1, by the way. So now we'll have n squared is equal to, well, we know that this reduces to the square root of pi over a, where a is going to be m omega over h bar. So that's going to become h bar pi over m omega whole thing squared. Yeah, something went wrong here. Because then I'll take the square root again. That's all of the fourth. So I don't know what happened. I'm not sure what happened, guys. But these are not agreeing. So if you stuck around for the whole 40 minutes, my sincerest apologies that I did not end up getting the correct answer. Put a dent in this piece of chalk, though. But again, that's why I wanted to do these videos. Just so you guys can kind of see, anyone who's thinking about going into physics or mathematics, and wants to kind of get an idea of some of the math they're going to run into and some of the rigor. It does get quite involved quite fast, especially in your senior year when you take quantum mechanics. So, all right, I'm going to cut the video here, guys. Sorry I didn't get the solution. I will be back. We will figure this out. All right, bye, guys.